Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC Lecture Series intended for the BSc Honours Physics students. We have been going through a set of lectures on optics. To start with, we had a course of lectures on geometrical optics. Then we moved on to the wave optics, wherein we discussed the conditions for constructive interference and destructive interference. Thereafter, now we move on to interferometers, especially the Michelson's interferometer, and in the syllabus to be covered or the idea of formation of the fringes without much of theory, determination of wavelength of a monochromatic source, and wavelength difference between two sources whose wavelengths do not differ by a large amount, refractive index, standardization of emitter. Now, these are the things we will try to cover in the lecture 22 and in the next lecture 23. Therefore, as far as the lecture 22 is concerned, the contents are as follows: Michelson's interferometer, working principle, formation of circular fringes, condition for bright fringe, localized fringes, and determination of wavelength of a monochromatic source. Here is the Michelson's interferometer, a part of which I discussed in the last lecture also. You have got a monochromatic source, something like a sodium vapor lamp. The light comes from the monochromatic source. It is incident on G1. It is a semi-silvered transparent glass plate kept at an angle of inclination 45 degrees with respect to the incident ray. This is the incident ray here. It subtends an angle of 45 degrees. Then the light ray that is incident here, because it is a semi-silvered mirror, obviously semi-silvered mirror means you have got about semi. That means partly the light is reflected because it is a mirror, partly it is reflected. What will happen to the reflected beam? The reflected beam will go towards the mirror at the top, that is M2, and it is a glass plate, as I told you. G1 is a glass plate, a semi-silvered glass plate. So, after partial reflection, there will be partial transmission also. Light transmitted will go through another glass plate G2 to the mirror M1. You have to comment about the mirrors M1 and M2. The mirrors M1 and M2 will be mutually perpendicular to each other. One of the mirrors is fixed, whereas the other mirror will be a movable mirror. The light that is coming back from the mirrors M1 and M2 will interfere with each other, giving rise to an interference pattern that can be observed by the human eye or through a telescope or some other detector. The same experimental setup will be shown in the next slide. It is called dividing phase. The reason it is called dividing phase because it divides the light ray into two parts. One is the reflected ray, the other is the transmitted ray. That is the reason why it is called dividing phase. It is nothing but a semi-silvered surface that forms the dividing phase. Same thing is shown here. You got a source here. They are called sodium fringes. That means you got a sodium vapor lamp. The light is coming and incident on the beam splitter. It is called a beam splitter because the beam gets split up into the two parts. One is the reflected part, other is the transmitted part. So it's called a beam splitter. And this one, the G2, this is a glass plate that you have got here, G2. It is called a compensator. It is called a compensating glass plate. I will tell you why it is called compensating glass plate in a moment. So the light ray that is passing here will be incident on a fixed mirror. The mirror that you have in the horizontal direction will be fixed at a particular position. It is called a fixed mirror. Whereas the other mirror that you have got here is a movable mirror. By means of a micrometer screw, the mirror can be moved. It can be moved very accurately, very precisely. The two things which are to be remembered are the two mirrors that I am talking about should be mutually perpendicular to each other. Then you will be getting this kind of fringes. What kind of fringes that you are observing? They are called the circular fringes. Obviously, they are circular fringes, similar to what you observed in the case of Newton's rings. So you will be getting circular pattern. If instead of the mirrors M1, M2 being mutually perpendicular to each other, instead of that, if they are slightly inclined, then you will be getting what are called, instead of circular pattern, you will be getting straight fringes, as you had in the case of, in the case of air wedge. You know, we have studied both the Newton's rings and the air wedge. In the case of Newton's rings, they are rings. So circular rings will be bright and dark rings will be obtained. Whereas in the case of air wedge, you will be getting straight bands. Or in the Fresnel biprism also, you will be getting straight bands. Dark band, bright band, dark lines and bright lines. Straight lines will be there. And here you will be getting this kind of straight lines when the two mirrors are kept inclined. Slight inclination will lead to the bright and dark bands. Let me now go back to the principle of the Michelson's interferometer once again. In Michelson interferometer, a beam of light from an extended source is divided into two parts. What I told you is, you know, you got the glass, one of the glass plates. It is splitting the light ray into two components of equal intensities by partial reflection and refraction. These beams travel in two mutually perpendicular directions and come together after reflection from the plane mirrors M1 and M2. The two beams obviously will overlap. The two, what is interferometer? What is the interference? Interference means the two beams should be interfering with each other. Similarly, the two beams that are coming from the mirrors and M1, M2, they should be overlapping with each other, giving rise to interference fringes, and they may be bright or dark depending upon the condition for constructive interference or destructive interference. The schematic of a simple Michelson interferometer, it goes as follows. It consists of what is called a beam splitter G1, a compensating plate G2, and two plane mirrors M1 and M2. The beam splitter G1 is a partially silvered plane mirror. The compensating plate G2 is a simple plain parallel glass plate having the same thickness as that of G1. It is to compensate the extra path travelled by the reflected ray. Now, why is it called a compensator? Now look at the diagram once again. You compare the two light beams. One light beam that is coming here is the initial light ray that is coming here. It undergoes refraction. From this point, what happens is this light ray goes in this direction. Whereas this light ray, it undergoes again a reflection here, a refraction here, and again comes back. It undergoes refraction and then comes here. It travels a path which will be equal to thickness of the glass plate. So it travels through 2 times the extra path that compared to the light ray that is traveling in this direction. Remember once again, up to this there is no path difference. The extra path traveled by the reflected beam is twice this path, twice the thickness of the glass plate. So that is the reason why you got a compensating plate. A compensating plate is kept in order that the effective distances traveled by the two light rays are identically the same. So let me repeat it once again. It is called a compensating plate because it is used to compensate the extra distance traveled by one of the light beams which is traveling to the top as shown in the diagram compared to the beam that is traveling in the horizontal direction. So to compensate that, you have got a compensating glass plate G2. So the compensator is kept here to compensate the extra distance traveled by one of the glass plates. That is the reason why you have got a extra path and a compensator and so on. The two plates G1 G2 are held at the same angle of inclination 45 degrees with respect to the incident beam. The mirror M1 is mounted on a carriage and can be moved exactly parallel to itself. You have the mirror here. M1 can be moved with the help of a micrometer screw. The distance through which the mirror M1 is moved can be read with the help of a graduated drum attached to the screw. Something like a traveling microscope. This can be the distance through which the mirror M1 is moved can be measured, whereas the mirror M2 is a fixed mirror. So the mirror can be moved to an accuracy of about 1000 angstroms, or in other words 0.1 micrometer. So such distances can be easily read. The plane mirrors M1 and M2 can be made perfectly perpendicular to with each other by means of fine screws attached to them. So the mirrors can be made exactly perpendicular to each other. That is important. If they are perpendicular, then you will be getting circular fringes. If they are slightly inclined, as you will see in the lectures to come, you will be getting, instead of circular fringes, you will be getting straight lines, as in the case of air bridge. The bands that you finally obtained can be seen by a telescope or by means of certain other detector. Monochromatic light from the source S is rendered parallel by means of a lens. You got a beam splitter, a partial reflection, all these things we have seen. The beam AC travels normally towards the plane mirror M1, reflected back along the same path and comes out along AT. T refers to telescope. And finally, you see the beam, the two beams interfering with each other, and what you observe through the telescope, that the light ray is coming along AT. The two beams received along AT are produced from the same source through division of amplitude. What do you mean by division of amplitude? The same beam, the intensity is divided, right? What is the difference, or what is the relation between intensity and amplitude? Intensity is nothing but it is directly proportional to amplitude square. So the intensity of the light beam, it is now split up into two parts. One is in the form of reflected beam going towards the top. The other is the transmitted beam. So the intensity is split up, or the amplitude is divided. So it is a division of amplitude, and hence they are coherent, because the two light sources that you will be having, the light rays coming from M1 and M2, they will be coherent, or they will give rise to two sources which can be called as coherent because originally the light beam is coming from the same source, yes, a single source. So, because of the fact that light is coming from a single source, it is getting split up into two beams. The sources are coherent sources, they interfere with each other. So, let us have a break at this point and we will resume at the break. Welcome back. After the break, we were seeing the construction and working of the Michelson's interferometer, and we will now move on to the formation of circular fringes. You had, in the case of Newton's rings, you had circular rings. Similarly here, you will be getting circular rings. As I told you some time back, you will be getting circular rings if the two mirrors M1 and M2 are mutually perpendicular to each other. They should not be inclined. If they are inclined, you will be getting parabolic or hyperbolic fringes. A part of them will be straight lines, or you will be getting a wedge-shaped film because the angle that will be appearing between the two mirrors which are slightly getting inclined. Therefore, when you want to get circular rings, circular fringes, that is the first thing that we want to have now. The two mirrors should be perpendicular to each other. The circular fringes are produced when the monochromatic light is incident on the mirrors M1, M2. They are exactly perpendicular to each other. The two light beams should be perpendicular to each other, or the mirrors M1, M2 should be exactly perpendicular to one another. If we look through the instrument, through T, the telescope, we see the mirror M1 directly. The point is, you see the mirror M1 directly, you see through the telescope, the light coming from this can be directly viewed, whereas this one is getting reflected and coming here, right? One of the sources, one of the light beams can be directly seen. The other one, the light beam goes here and getting reflected, and again reflected and so on. Now, therefore, you got two light beams which are coherent with each other. So, circular fringes are obtained when the two mirrors are perpendicular to each other. If we look directly through the instrument T, we see the mirror M1 directly, and in addition, we will see the virtual images M2 prime of the mirror M2 formed by reflection in the glass plate G1. It means that one of the interfering beams comes from M1, the other beam appears to come from the virtual image M2 prime. This point is important. So, you have interference occurring or interference arising due to M1, the other beam that appears to come from the virtual image M2 prime. So, one is M1, the other is M2 prime. So, M1 is here, M2 prime is here. These two can be considered to be separated by a distance d, and in the field of view, when you have an eye here, in the field of view, sources are S1 and S2. S1 and S2, one of them is the one that you directly see through the telescope. The other one is the virtual source that you obtain because of reflection. Now, the distance that separates this is 2d. If this is d, this is 2d. The angle subtended by this is theta. You have the angle that is subtended at the eye by the light ray that you have got here is theta. That is theta here. This is small d, this is 2d, twice the distance d that separates M1 and M2 prime. Therefore, let me go back. If the two arms of the interferometer are equal in length, image M2 prime coincides with mirror M1. If M2 prime and M1 do not coincide, the distance between them is finite. That means you take them to be equal to D. That is the distance between M1 and M2 prime. That is the distance D. This is what I am trying to tell you. This is the distance D. This will be 2D. So, if a light ray S1 coming from M2 prime, S2 due to reflection at M1, the virtual images are separated by a distance 2D. And if the distance is 2D here, the angle is theta. So, the path difference between these two will be 2D cos theta. The horizontal distance will be 2D cos theta. Therefore, you will have the observer looks at the system at an angle theta, because I showed the angle of inclination theta. The path difference between the two beams will be 2D cos theta, and again there will be a dissimilar reflection, because the light that comes from M2, one of the mirrors, one of the glass plates, goes to T, it undergoes a dissimilar reflection, that is rarer to denser reflection, and therefore, as all of you know by now, whenever there is a reflection that is taking place, when light ray is going from denser into rarer, then or rarer into denser reflection, there will be a phase change of pi that occurs. I showed you a long time back that when a light ray is incident on the interface of a glass plate separating air and glass from the rarer medium, when the light ray tries to go into a denser medium, there will be a phase change of pi, or a path difference of lambda by 2, because a phase difference of 2 pi corresponds to a path difference of lambda. A phase difference of pi corresponds to a path difference of lambda by 2. That is the reason why I got lambda by 2 here, right? A phase change of pi will lead to a path difference of lambda by 2. Therefore, apart from 2D cos theta, that is the path difference between the two interfering beams, because of the dissimilar reflection, because of the fact that one of the light rays among the two light rays you are talking about, which are trying to interfere, one of the light beams, it tries to go from rarer into a denser medium after reflection. Because of that, there will be additional phase difference of pi, or a path difference of lambda by 2. So, the total path difference will become equal to 2D cos theta plus lambda by 2. So, all of you know by now, if the total path difference is lambda, or even is 0, right? If there is no path difference at all, if the crest of one wave coincides with the crest of the second wave, or a trough of the first wave coincides with the trough of the second wave, the path difference is 0. Or if the path difference is lambda, lambda also then will correspond to a crest meeting a crest, or a trough meeting a trough. 2 lambda also correspond to the same thing. Therefore, in general, if the total path difference is integral multiple of lambda, and the integer may be 0, 0 means there is no path difference, then it may be 1 or 2. 1 means the path difference lambda, 2 means 2 lambda. Therefore, if the total path difference satisfies the condition, namely 2D cos theta in this case plus lambda by 2 is equal to m lambda, that will lead to what is called constructive interference. That is the condition for bright fringe. Is that right? The condition of bright fringe, the condition is given as follows here. So, you get circular fringes because you are talking about the angle theta, and I showed you in the earlier diagram that you saw, you have got a theta here, and so at a point here, at all the points corresponding to theta, you will be getting a bright ring or a dark ring, and so the rings that you are getting here will be circular in shape. Therefore, in Michelson interferometer, the point to be noted is, if the two mirrors which are kept, if they are perpendicular to each other, that is M1 and M2 are made perpendicular to each other exactly, then you will be getting circular fringes, the bright fringes, for a given wavelength and for a separation d, and the order is m, angle theta is constant. Because angle theta is constant, we are getting a circular ring. This means the fringes are circular in shape. They are called fringes of equal inclination. Why are they called fringes of equal inclination? Because the angle theta is the same. In case the mirror M1 coincides with the virtual image M2 prime, D is equal to 0. The path difference between the interfering beams will be lambda by 2. If I make D equal to 0 in the earlier expression, D is equal to 0, the path difference will be only lambda by 2. If the path difference is lambda by 2, what I would like to tell you is, if the distances separating the two from the central plate to the mirror M1 and to the mirror M2, if the distance is exactly the same, so the effective path difference, if it is lambda by 2, if the path difference is lambda by 2, what will happen? That means lambda by 2 means what? Crust is meeting a trough, right? Or a trough is meeting a crust, vice versa. If a crust and trough meet, there will be destructive interference. If there is a destructive interference, what will happen? There will be darkness. That is what I am showing now. So, there will be darkness. So, if the effective path difference is lambda by 2, as I showed here, the path difference between the two interfering beams is lambda by 2, then the center will appear to be dark. Okay. Then what I now do is the following. I move one of the mirrors. You know, one of the mirrors is fixed. The other mirror can be moved. If I move the mirror by how much? I want to have brightness here. What should I do? I should move the mirror. I should eliminate lambda by 2. How will you eliminate lambda by 2? You move the mirror through lambda by 4. If you move the mirror by lambda by 4, because the light beam goes and comes back. So, twice the lambda by 4 will be lambda by 2. Therefore, if an additional path lambda by 2 is introduced, additional path difference is introduced, then the region will appear to be bright. If one of the mirrors is now moved through a distance lambda by 4, the path difference introduced is lambda by 2. Therefore, a maximum is obtained. Maximum means brightness, right? You have a bright region here. But on the other hand, if the path difference is lambda by 2, as I told you earlier, we obtain a minimum at the coincidence position, and the center of the beam will be appearing dark. This is what I showed you here. The beam is dark when the path difference is lambda by 2, right? If the path difference is lambda by 2, it is dark. Then I move the mirror through a distance lambda by 4. Moving it by lambda by 4, the path difference changes by lambda by 2. Therefore, the center becomes bright. By moving the mirror through another lambda by 4, what will happen? Whenever a mirror is moved through lambda by 4, you introduce a path difference of lambda by 2. An additional path difference of lambda by 2 will lead to, again, the opposite thing, namely, from bright you go to dark. So, therefore, you get the dark ring here. That is what I showed you just now. You get a bright ring, and then brightness and darkness, and then again the center becomes dark, similar to what you have here. Dark, again the center becomes bright. Therefore, every path difference lambda by 2 that is introduced. How will you introduce path difference lambda by 2? That means the mirror should be moved through a path through the length lambda by 4. So, by changing the thing by mirror's position by lambda by 4, you get alternately bright and dark rings. They are the so-called Newton's rings. Therefore, now we move on to the summary session for the lecture 22. The summary goes as follows. The Michelson interferometer can be used for measuring the wavelength of a monochromatic source. This is one of the applications. In order to perform the above, one needs the formation of circular fringes. Circular fringes are obtained by having two plane mirrors exactly perpendicular to each other. The two sources S1 and S2, one is the real source, the other is the virtual source, are made to interfere with each other. And the questions are as follows. Explain the working of Michelson's interferometer. How do you obtain circular fringes using Michelson's interferometer? State the condition for the formation of bright fringes. With this, we come to the end of lecture 22. We will move on to the lecture 23, in which case we will be seeing what are called localized fringes and the different applications of Michelson's interferometer. The rest of the things we will see in the next lecture. Thank you.